Okay, so in our 9th lecture of real analysis, we are going to look at Koshi sequences and subsequences. And these are terms we'll be defining in the course of the lecture. So the main goal, as I've alluded to in previous lectures, is that we want to find a way to describe convergent sequences that doesn't explicitly mention what the limit is. So in our current definition of a convergent sequence, the criterion for that is explicitly in terms of the limit A, right? We need to know the limit A to say that the sequence is getting arbitrarily close to that limit in order to say that the sequence converges. We would like a way of describing a convergent sequence that doesn't explicitly mention that limit A. And why do you want such a criterion? Well, I mean, it can be hard to determine what a sequence might be limiting to, even if we're highly confident of the convergence. Okay, so even if you're highly confident that you have some sequence and you feel very confident maybe by just looking at some plugging in a bunch of values and looking at the data, seeing that the sequence seems to be settling down to some value, it can be hard to know what that value might be. So it'd be comforting to have some way of determining that the sequence converged without actually knowing precisely what that limit is. So that's of theoretical interest in any case, but it can sometimes be of practical use as well. So for example, and there's examples like this on the homework 4 that you're working on. So you'll see this in action. But if you have a recursively defined sequence like this, so let's say you're given some initial A1, and then you have this recursion relation which tells you how to get A2 from A1 and how to get A3 from A2, etc., where this F is an algebraic expression. Okay, so using plus and times and division and subtraction, things like that. Then if this sequence here of the ANs, if we know that converges, then what we can do is, because this F is an algebraic expression, we can just use the algebraic limit theorem, right? This AN plus 1 is going to converge to the same limit as AN, and so we'll just have A equals F of A from this equation. So basically just take the limit on both sides here, you get A equals F of A, and you can possibly solve for that limit. Okay, so even if it seems like it'd be kind of hard to tell what the limit is from just looking at the actual sequence itself, right? Each successive term, you can nevertheless compute the limit from this information in a nice simple way, just solving an equation. However, this method you can run into trouble with this method. So it's possible to have a recursion like this, take the limit and solve for A, but that A actually not be the limit of the sequence. And the problem is you can get an answer A out of this even if the sequence actually doesn't converge. So just because you get some A out of here doesn't actually mean that the sequence converges. You need to know ahead of time that the sequence converges in order to be confident that the A you get out of this is the limit. Okay, so you can get into trouble if you don't know that the sequence converges first. So this is a particular practical, at least you can find practical examples of situations like this, where you need to know the convergence ahead of time in order to actually solve for the limit. Okay, so this is the goal and the motivation for the lecture. So this goal, there is a way to do this, and this is due to Cauchy. So Cauchy has a definition which is equivalent to that of being a convergent sequence. It's just not obvious, logically speaking, that it is equivalent. Okay, but let's first discuss what Cauchy's idea is. Okay, so here's Cauchy's idea. So remember, we're trying to characterize when a sequence is converging without actually talking about the limit itself. Okay, so one way you can think about this is to ask, how can the sequence itself, okay, without any reference to the limit, right, just the sequence itself, just looking at the elements of the sequence, how can we determine when it's converging? So in other words, how would the sequence itself be able to tell when it's converging to some limit? Okay, so just the intrinsic properties of the sequence itself. is what we're focusing on here. And so if you think about this picture, right, so we know our sequence is converging, right? So there is some limit A here. We're not going to reference that limit, but it's helpful to put it in the picture, right? So you have some sequence. You start here, and then maybe you jump to here and here. And you're jumping around a bit, but then you're getting closer and closer to this A. But forget about A and just think about the elements of the sequence, right? What are the elements of the sequence feel? The elements of the sequence start feeling very crowded, right? They start feeling very claustrophobic because they're all getting so close together, right? They're all getting close to this A, so that means they're all getting close to each other, right? So it's getting very, very crowded and very uncomfortable in here, right? Not a lot of personal space for the elements of the sequence in here. Okay, so the basic answer, sort of obvious answer here, is that we have convergence when the tail of the sequence, right? So so at some point in the sequence, let's say when we're at A sub big N, right? For all of the elements of the sequence past that point, that they all feel really crowded, right? They're all bunched up together. Okay, so all of those things after that A sub N, you can call that the tail of the sequence. So when the tails of the sequence are bunching up closer and closer, right? Ever closer and closer. And so this leads to the following definition. Okay, and so this is the definition of a Koshi sequence. So a sequence is a Koshi sequence when the tail of the sequence gets bunched up like this. Okay, so the basic punchline here is going to be that every convergent sequence is a Koshi sequence and vice versa. Okay, so this is a major theorem called the Koshi Criterion. Okay, so this is the theorem of the Koshi Criterion. That what we're describing here is really just a convergent sequence in disguise. Okay, so we're really just trying to describe this idea of being convergent without referencing the limit A. But we really, we have to prove that this definition of Koshi sequence here is equivalent to the definition of convergence. And that will be sort of the major project. Okay, so right now we have to pretend that we're just defining some possible property of a sequence, that the sequence is what we call a Koshi sequence, and then later we're going to show that this is the exact same thing as being a convergent sequence. Okay, so right now this is just some property this sequence can have. It may or may not be related to convergence, but ultimately we're going to prove that it exactly coincides with that. Okay, so anyway, a sequence then is a Koshi sequence if for any given epsilon. Okay, so this epsilon is going to measure how claustrophobic it is at the tail of the sequence, right? So how squeezed together those elements of the sequence are at the tail. Okay, so basically this epsilon greater than 0, we're just going to say everything, after some point in the sequence, so all of the tail elements are within epsilon of each other. Okay, and that's for any given epsilon. So this is saying things are becoming more and more crowded, arbitrarily crowded. Okay, so for all epsilon greater than 0, there's a natural number capital N. So this will be after this point in the sequence, right? So for m and n bigger than or equal to n of this big N, we have that a sub m and a sub n are within epsilon of each other. Okay, so everything in the tail of the sequence, starting at a sub big N and beyond, that they're all squeezed in to within epsilon of each other. Okay, so everything is very crowded past this point in the sequence. Everything falls within epsilon. Okay, so let's show right away that this has something to do with convergence, as it should. Okay, so here's the easy implication in the Cauchy Criterion. So again, Cauchy Criterion just is going to say that a Cauchy sequence is exactly the same thing as a convergent sequence. Okay, so one way is easy. A convergent sequence is a Cauchy sequence. Okay, the reverse implication that this Cauchy sequence is a convergent sequence is harder, and the reason it's harder is because a Cauchy sequence, there's no proposed limit, right? You have to figure out what the limit is. You have to somehow produce a limit for this thing to converge to, and so that's kind of the heart of the matter in proving the Cauchy criterion, figuring out how to propose a limit for a Cauchy sequence. But the other way is much easier. So here's a first theorem on this matter. So if a sequence is convergent, then it's Koshi. So convergent sequences are Koshi. Okay, and let's prove this. So suppose that we have a convergent sequence, AN going to A. So we have to show our sequence is a Koshi sequence. That means we have to show that for all epsilon greater than 0, there is an n such that blah, 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 right? So we need epsilon greater than 0 to be given. So we suppose we have our sequence converging to A, and we let epsilon greater than 0 be given. Okay, now, so the basic thing is we have to figure out what this n is going to be, this big N, so that the elements of the sequence past that n are close to each other. And so sort of schematically, so this is my scratch work, my brainstorming. I'm trying to figure out, right, I want the AM to be close to AN. And so I want AM to be close to AN, and what I have is that my sequence is converging to A, right? So after some point in the sequence, all of the A's are going to be, all of these A's, the A sub n's, right? So A sub m and A sub n, they'll be close to A. Right? So what I have is that A sub m, that should be close to A after some point, right? And A sub n should also be close to A. So sort of by transitivity, if AM is close to A, and A is close to AN, then AM should be close to AN. Okay, and so what you can do to deal with this is the triangle inequality. So AM minus AN, right, what I can just do is I can insert an A in there. So this will be this plus A minus AN. And that's going to be less than or equal to, right, I have the sum of two things, so that'll be less than or equal to the absolute value of the sum. And I can make each of these things I can make as small as I want, right? Ultimately, I want this whole thing here. I want that whole thing to be less than epsilon, so I can just make each of these, as long as I can make each of these less than epsilon over 2, right? Then this will be equal. That'll be equal to epsilon, and the whole thing will be less than epsilon. All right, so I just need to make this less than epsilon over 2 and this less than epsilon over 2. So in other words, I just need to go out to the point in the sequence at which, right, because we have convergence, just go out so far that the A sub n's are less than epsilon over 2 away from A. Okay, so by the convergence, so there is a big N in natural numbers, such that when n is bigger than or equal to that n, that implies that the distance between the AN and A is less than epsilon over 2. Then if little m and little n are bigger than or equal to that big N, right? So now basically, right, so for any single n here, we have this condition. Now I'm going to take a look at two of them, right? So I'm going to have AM past the big N point and AN past the big N point, and we're going to run through this computation here. So let me give myself some room here. If those things are past the point n in the sequence, right, so this is just going to be my big N here in the definition, and then I just have to run through this. If that's the case, we have the following computation. We can compute that the distance between AM and AN, that is equal to AM minus A plus A minus AN. That's less than or equal to AM minus A plus absolute values AN minus A. That's less than epsilon over 2 plus epsilon over 2, and that is less or equal to epsilon. Okay, so that is the proof that our convergent sequence is Koshi. Okay, so this establishes a link, at least in one direction, between the notion of convergence of a sequence and a sequence being Koshi. So the ultimate theorem that we're going to prove, and we're not going to prove it in this video, but this is the goal. Okay, so this is our goal. And this is called the Koshi Criterion. Is that in fact a sequence is convergent if and only if it's Koshi. It's a Koshi sequence. Okay, so we just showed that convergent implies Koshi, and we need to show the other direction, that Koshi implies convergent eventually. Okay, and as I said, the difficult part of this is when you have a Koshi sequence is to actually produce a limit, right? You have to say, you have to at least theoretically say, theoretically justify that there is some limit to which the sequence is tending. Now, so this criterion is called the Cauchy Criterion. According to Abbott in the text, Cauchy himself didn't prove this. He kind of thought it is obvious or something. He sort of took it for granted, and it was only later generations of mathematicians who really provided a careful proof of it. And the reason is that, so in order to produce this limit, okay, so when you have a Cauchy sequence, in order to produce a limit, this is really going to depend on the completeness of the real numbers. So as you might expect, sort of not surprising. So the reason that there is going to be a limit is because the real numbers are complete. There's no holes in the real numbers, right? There's got to be a limit there. So you need to know something about the nature of the real numbers, which was kind of only worked out after Cauchy's time. Mathematicians had to keep working their way backwards to the foundations. So Cauchy had all these notions of epsilon delta proofs, continuity, and convergence, and all these things, but didn't ultimately have the bedrock foundation in the real numbers. But had more of an intuitive sense, robust intuitive sense of them. But anyway, so maybe we should. So I think it'd be a good exercise to sort of, convince ourselves why Cauchy thought this was kind of obvious, right? With his intuitive sense of the real numbers. So why should we believe that a Cauchy sequence is a convergent sequence? I think it'll be profitable to take a look at that. That'll give us some motivation for moving forward. Okay, so here's my best guess for what I think Cauchy might have been thinking, sort of the lines along which Cauchy was probably thinking that led him to believe that a Cauchy sequence must be convergent. So we think about the definition of it being a Cauchy sequence. There has to be an n1 such that when your m and n are past that point in the sequence, that the m minus an, or the distance between am and an, is less than 1. Right? So we can take epsilon equal to 1. Right? And so in particular, if we take m to just be this n1, so we take m to be that n1, this says that after the point n1 in the sequence, everything past that point is within one of that an1, right? So in other words, the entire sequence after this point is trapped within one of an1. Okay, so that sort of puts a hard bound on where the sequence is. So let me see if I can draw a picture of this for us. Okay, so here's the picture. We have our an1 here. We have go out 1 to the right and to the left, and all of the an's past that the big n1 point they're within this interval. Okay, so they all fall in here. So some of the sequence could possibly fall outside, but then the rest of the sequence falls within this interval here. And in particular, I can just note here that this, more or less, this picture automatically kind of intuitively implies that a Koshi sequence is bounded, right? So we have, you know, a finite number of terms which might fall outside of this little window here, but we can, you know, but a finite number of terms is always bounded, and then we have the infinitely many remainder terms after this point in the sequence, all falling in this interval of length 2 here. So that clearly kind of clearly at least intuitively bounds all of the elements of the sequence. So we might kind of note here as something to prove later is we should try to prove that Koshi sequences are bounded. Okay, so Koshi sequences are bounded, and we'll prove this later. Okay, so this is one thing. So we have this particular picture here, but then also, right? So we can kind of keep going here. So there's also going to be an n2, which we can say is bigger than or equal to n1. So some point further out in the sequence, right? Where when m and n are bigger than or equal to that n2, then am minus an is less than 1/2, say. Right, so again, in particular, if we take this am to be n2, then an2, the distance between an2 and everything further out in the sequence is less than 1/2. Okay, so one of these an1s here might be an2. So let's see if we have an2 here. Then what we know is that all of the sequence has to fall within 1/2 of that thing. So let's see. So we have this kind of tighter bound. After this n2 point in the sequence, everything beyond that has to fall in there. Okay, so we might have some terms coming over to here, but clearly, but they have to fall within those green bounds. And then you can see how this clearly sort of keeps going, right? So there's going to be some an3 point in the sequence further on, right? So an3 such that we can have put even tighter bounds on here. So it would only go out like a third in each direction. The entire sequence has to be trapped within that. And then I'm going to kind of run out of colors here in a second. Let's see, I could do pink. And then an an4, which is within there somewhere, right? So the entire rest of the sequence is trapped in these in the purple, and then maybe we have like an an4 somewhere like here, and everything is going to be trapped within that part, right? So we keep just getting these tighter and tighter bounds, or trapping the sequence further and further, and right, as we go down, these intervals keep shrinking, right? So first we had 1, then 1/2, then a third, and then a fourth, and we'll keep on going down and down and down until we're really zoomed in, right? So we're just zooming in further and further here, and because our real line is complete, right, continuous, no gaps, the further we zoom down, we're actually going to see something down there, right? There's got to be a real number down there after we have zoomed in sort of infinitely far, so to speak. Okay, so that, I think this is probably, roughly speaking, what Cauchy's intuition was, that we can just do this sort of zooming in thing on our sequence, and we're going to see something down there. And of course, since, right, no matter how far we zoom in here with these intervals, the entire sequence, right, the entire tail end of the sequence is trapped within that really small interval. Okay, so as long as there is something ultimately down sort of at the bottom there, the tail end of the sequence is going to be arbitrarily close to that thing. Okay, and so that would say that the sequence converged to that thing, as long as we knew that something was actually all the way down at the bottom, so to speak, of all of those intervals. And so what you can kind of see here is that basically one strategy, so sort of most obvious strategy for the proof of the Koshi criterion, right, for the proof that Koshi sequences are convergent, would be to use the nested interval property. Okay, so I wrote that down. So there's going to be a number of ideas for possibly proving Cauchy's criterion. The nested interval property, kind of the most obvious one from this picture, you can just change these open intervals to closed intervals, right? If these, right, if you have a less than sign, that implies a less than or equal to sign. So you can just change these to closed intervals, and then you have this zooming in closed intervals sort of picture that you can definitely make work to prove that there's a limit at the bottom, right? So you have the intersection of all of these closed intervals. There's going to be something down in that intersection. You can prove that there's a unique thing in that intersection, and then you have to prove that the sequence converges to that thing. Okay, so that's sort of the most obvious idea. It makes it very clear, I would say, that Cauchy sequences have to be convergent sequences. Okay, so I'd say this sort of rough picture outline of an argument and pointing to an actual theorem that we can use puts the obviousness of this Koshi criterion within 95%. We should be at least 95% confident that this theorem is true at this point, maybe 99. Okay, but of course, since this is the most obvious idea for proving the Koshi criterion, this is never how any books prove it. They use something more complicated, which is actually going to be the third thing on the list, because that's the way we're going to do it. That's how the book does it. I might assign as an exercise to prove the Koshi criterion. I might walk you through kind of steps of a proof of the Koshi criterion using the nested interval property. Okay, so there's some other ideas for proving the Koshi criterion. So the basic thing that we need to do to prove this, right, is we have our Koshi sequence. What we need to do is show that there is some limit, right? We want to show that a Koshi sequence is convergent, so we need some proposed limit. Well, one theorem that we've learned, which is a consequence of completeness, of the completeness of the real numbers, is the monotone convergence theorem, right? If we have a bounded monotone sequence, then that has to converge to a limit. And so that's a predecessor of this Koshi criterion here. It's a situation in which we can say that a sequence converges without actually saying what the limit is ahead of time. So another idea here would be to try to use the monotone convergence theorem. And so for this, what would we need to make the monotone convergence theorem work? Well, the basic idea would be your Koshi sequence might not be a monotone sequence, right? So for example, so any convergent sequence is a Koshi sequence. So for example, say like -1 to the n plus 1 over n. And so if we set an equal to that, that's clearly a Koshi sequence and it's converging to 0. But it's not a monotone sequence because it's sort of jumping back and forth between positive and negative numbers. Right, so here we have a Koshi sequence which is not monotone, so it seems like monotone convergence is kind of useless, right? Right, and maybe I should write down a few terms of this sequence. We have a 1, -1/2, 1/3, -1/4, and then 1/5, etc. Right, so that's what our sequence looks like. It's not monotone because it's doing this hopping around, but what we see here in this sequence is that there's a kind of subsequence. There's a sequence inside this sequence which is monotone. Actually, there's a couple that you can spot, right? So we have this decreasing sequence, 1, 1/3, 1/5, 1/7, and that converges to 0 and is a monotone sequence, right? And we also have this increasing sequence, -1/2, -1/4, -1/6, and that also increases to 0. So this gives us a kind of idea to use the monotone convergence theorem is to sort of look for a sequence inside our sequence which is monotone. Okay, so if we find a sequence inside of our original sequence, which is monotone, then in order to use the monotone convergence theorem, we need to say that this sequence inside of our sequence is bounded. But remember, we noted that Koshi sequences are probably bounded, right? So that's just something we have to prove. So then you want to use that Koshi sequences are bounded. So use that Koshi implies bounded. And what you get is a limit for this subsequence, okay, for this sequence that's inside this sequence. So you get a limit of the subsequence and then you need to show, that this limit is not only a limit for the subsequence, but it's a limit for the original sequence, okay, which we observed in this example. So each of our subsequences both converge to 0, and 0, of course, is the limit of the full sequence, right? So this would be, you could make this work in general. If you can find a monotone sequence which converges inside your Koshi sequence, then your original sequence is going to converge to that limit. So you need to show that this limit is the limit of the original sequence. Okay, so that would kind of be a natural progression of ideas there. So your initial idea being try to use the monotone convergence theorem. Obvious problem is that Koshi sequences don't have to be monotone, but you sort of look inside your sequence for a monotone sequence, extract the limit of that from the fact that Koshi sequences are going to be bounded, and then use that limit of that subsequence and try to show that that is the limit of the original sequence. Okay, so this sort of brings up a fact. So here's another note, is something we're going to prove, is that if a subsequence, and this is a term I have to define, I haven't defined this yet. Okay, so I'm trying to walk us through, the ultimate goal here is to prove the Koshi criterion, but trying to prove this, sort of coming up with ideas for how to prove this, leads us to other notions, to consider other notions. So this is sort of motivation for this idea of a subsequence. So what we're going to show is that if a subsequence, once we define that, of a Koshi sequence converges to some limit, to a limit L, then so does the original sequence. Okay, so Koshi sequences, the property of being Koshi, and it looks like I misspelled Koshi here, too many C's or something. So the property of being Koshi allows the sequence to have this kind of hereditary property. If a smaller sequence inside the sequence converges, then the whole sequence has to converge to that. Okay, so these notes will be things that we want to prove later. Okay, so that would be another way to go about proving the Koshi criterion. The final way to prove the Koshi criterion is the least obvious way, and this is using what's called the Bolzano Virustras theorem. It's also the least obvious way to spell, the hardest to spell, and the least obvious. Okay, so the Bolzano-Virustras theorem is a totally different theorem that I haven't talked about yet, but it says that a bounded sequence has a subsequence, has a convergent subsequence. Okay, so the Bolzano-Virustras theorem says that a bounded sequence has a convergent subsequence. Okay, and you should think about the facts that we know about, or whether that we're going to prove about Cauchy sequence. So look at these two notes. And so Cauchy sequences are bounded, and if you have a subsequence of a Cauchy sequence converging to something, then so does the original sequence. So take those two notes and the Bolzano-Virustras theorem and see if you can, work out how the Koshi criterion follows from all that information. So I'll give you. So just take a couple seconds and make sure you can see that implication. So basically just read this note and this Bolzano-Virustras theorem and see if you can see how the Koshi criterion follows. I just realized I omitted the word does, so that should have spontaneously popped up there. Okay, so this Bolzano-Virustras theorem, this is something we're also going to have to discuss. So this is the least obvious way of proving the Koshi criterion, but since analysis books want to talk about the Bolzano-Virustras theorem anyway, they talk about that first and then deduce the Koshi criterion from it. So it's sort of the least amount of work if you want to talk about the Bolzano-Virustras theorem anyway, to just get the Koshi criterion as a corollary in a way of the Bolzano-Virustras theorem and the other properties of Koshi sequences. It's definitely not the most obvious proof, though. Okay, so you get this economy in terms of the logic, but in terms of the motivation for where the proof came from, it definitely seems like it's this, sort of difficult, it makes Koshi sequences and the Koshi criterion seem harder than it actually is. Okay, so there's these multiple routes to proving the Koshi criterion. Our book takes the least obvious route, like many other books, but I just wanted to, make sure to get across that, there's more than one way to get at a mathematical result. This is sort of multiple ways of sort of looking at the same thing. And definitely this is not an obvious way of going about proving this. So if it doesn't seem obvious, then that's par for the course. Okay, so in order to wrap all this up, ultimately, again, the goal is to prove the Koshi criterion. The way we're going to do it is by using the Bolzano-Virustras theorem. And in order to use the Bolzano-Virustras theorem, we need to know that our Koshi sequence is bounded, and then we need to know something about how subsequences of Koshi sequence are related to the original sequence. Okay, so we need to first prove that Koshi sequences are bounded. And we need to define carefully the notion of subsequence of a sequence. And these two items we'll do in this video. And then in the next video come the more substantial proofs. So the third item is the first proof there, which is that if you have a subsequence of a Koshi sequence converging to a limit, then the full sequence itself actually converges to that same limit. And then we'll prove the Bolzano-Virustras theorem. And from that, it's going to follow that the Koshi criterion will then follow from that. Okay, so I'll probably put that at the end of this list. Okay, so this is the plan. All right, so in the rest of this video, we'll prove that Koshi sequences are bounded first, and then we'll move to discussing the notion of a subsequence, and that'll wrap this video up. And in the next video, we have a couple proofs. The proof of the Bolzano-Virustras theorem is going to take just a little bit. The idea is really not that hard. It'll take a little bit to write down the proof. And then we'll again state that how the Koshi criterion follows from all of that. Okay, so first thing on the to-do list is this theorem. Okay, so we have the theorem that Koshi sequences are bounded. Of course, we know that convergent sequences are bounded, so given that Koshi sequences are supposed to have something to do with convergence, we shouldn't be that surprised. So this is one way in which before we prove that Koshi sequences are convergent, we can see that Koshi sequences are at least similar to convergent sequences. All right, so here's the proof. So it's that picture that I drew before, right? So after some point in the in the sequence. So we'll have a big N. After that point, everything is going to be within a distance of 1 of this thing. So we're going to have a n plus 1. Sorry, not a n plus 1. A sub n plus 1. And then a sub n minus 1. Right? The whole sequence after that point is going to be in here. And then we just have a finite number of outliers out here. So we have a1, a2, a3, etc. up to a sub n, actually this time a sub n minus 1. Okay, so we'll just need to sort of bound all of these things, and then everything else is within a distance of 1 of a sub n. So if we take, right, so 0 is going to be in here somewhere, right, so let's say 0 is here. All we have to do is make sure we take all of this stuff into account. So the furthest that this stuff can go is wherever a sub n is. So maybe I'll put 0 actually on the other side, sort of illustrate this. So maybe 0 is over here. Okay, so we'll have to take the absolute value of a sub n, that'll get us here, and then we have to go one further than that, right, to be ensured that we have all of this stuff. And we also have to take into account the absolute values of all of the outliers, right? So our m that we're going to bound this by, right? So we're going to say that all of our a sub n's are less than or equal to the max of all of the absolute values of the a1 through a sub n minus 1, and then we'll have absolute value of a sub n plus 1. Okay, so this conclusion just comes from sort of studying this picture here. So first, we'll say that all of our sequence past the capital N point is within 1 of a sub n. Okay, so because our sequence is Cauchy, so there is n in the natural numbers, such that when m and n are bigger than or equal to that capital N, such that implies that a sub m minus a sub n is less than 1. So in particular, little n bigger than or equal to big N implies that, right, this, by setting, so just parenthetically, by setting little m equal to that big N. Okay, because big N itself is one of these little n's. Okay, so we can set little m equal to that big N. Okay, so then define capital M. This is going to be our bound for our sequence as being the max of A1, A1's absolute value up through A capital N minus 1's absolute value, and then the absolute value of A sub n plus 1. Okay, and then we just have to say that the absolute value of the a sub little n's, is less than or equal to this number. Right? So when little n is between 1 and capital N minus 1, that's obvious, right? Because we have, right? Because those numbers appear in this list for the max. And then we'll have to use a little argument for the other values of n. So the infinitely many values of the a sub little n that fall into this interval will have a different argument. So let's say if little n is equal to 1, up through big N minus 1, then we have absolute value of a sub n is less than or equal to m by definition. If, on the other hand, all right, so I'm going to erase this picture now. And we already have our m written down, so I don't need that. So if, on the other hand, little n is bigger than or equal to big N, then what I need to say is that the absolute value of a sub n, that is bigger, that's less than or equal to this, this m, right? And so what I'm going to say is that it's less than or equal to this number, and that's going to be less than or equal to that max, right? So remember, our picture was my an is here. I have this interval of length 1 around it, and my an, I want to sort of bound that. And my absolute value of a little n here, that's just the distance of it from 0, right? And so I can measure to a sub little n, that's going to be in here somewhere. So I can measure that distance indirectly by going from 0 to a big N, and then from a big N to a little n, right? In other words, it's just the triangle inequality. So formally, I can say this is an minus a big N plus a big N. That's less than or equal to this plus a big N in absolute value. And we know that this is less than 1, right? So we have this thing is less than 1 here. So this is less than absolute value a big N plus 1, and that's less than or equal to m. Okay, so in either case, we have that the a sub n's. So in any case, the absolute value of the a sub n's is less than or equal to m, and so the sequence is bounded. All right, so Koshi sequences are bounded. So that's item 1 on our list. All right, so the second thing on the list and the last thing we're going to talk about is the definition of a subsequence. We'll just clarify the notion of subsequence, and then in the next video, we'll have some more heavy-duty proofs to discuss. So the notion of a subsequence is fairly simple. If you just have a sequence, so you just imagine a sequence like this, all the things laid out, a subsequence is gotten by just going along this list left to right, just picking things out, right? So you have to go strictly left to right. Okay, so I can take a subsequence. So I start somewhere, let's say A2. So start at A2, and then I just skip over as much as I want, as long as I'm skipping strictly to the right. Right, so I can pick, A5, and then I could possibly pick A6 next. So that's strictly to the right, and then I keep going like that. Right, so that is the idea of a subsequence, and that's just the definition that I'm going to write down. Okay, so that's the whole idea of it. And just colloquially, you can just say a subsequence is just a sequence that's sitting inside of your sequence. Okay, so here's the definition. We have our original sequence, right, as you can picture it like this, and we want to pick out this sequence inside of our subsequence, right? So what we have is these numbers 2, 5, 6, 8, right? And we're always going strictly to the right, so that sequence of numbers has to be increasing. Okay, so we're going to have this other sequence of natural numbers, n1, n2, etc. And so in this case, n1 is 2, n2 is 5, n3 is 6, n4 is 8. Okay, so we have this strictly increasing sequence of natural numbers. And then our subsequence is exactly the a sub n k's. So this index on the ends, right? So we have our 2, 5, 6, 8. Right, each of those is labeled by an index itself. So 2 is the first one, 5 is the second one, 6 is the third one. So our sequence is labeled by that auxiliary index k. Right, so we have k going from 1 to infinity, and our sequence then looks like this, and that's called a subsequence of our original sequence. All right, so a little bit maybe annoying to write that down, but the basic idea should be pretty clear. You'll know a subsequence when you see it. It's just going strictly to the right, just sort of picking terms out of our sequence as long as you're going strictly to the right. Okay, so just to be totally clear about this, as an example, if we take the 1 over n sequence, 1, 1/2, 1/3, 1/4, subsequences, a couple subsequences examples would be like the 1 over n squareds, right? So you just go out to the ends that are squares. So you have 1, 1/4, 1/9, 1/16, 1/25. Or 1 over powers of 2, 1, 1/2, 1/4, 1/8, 1/16, right? You're always going strictly to the right there. But some examples that are not subsequences would be if you skip around. So if you start like 1, 1/3, 1/2, right, going back like that, that's a no-no. So that automatically disqualifies that as being a subsequence no matter what comes after it. And then no repeats either, right? You have to go strictly to the right, so no staying on the same thing. So if you do 1, 1, that's automatically not a subsequence, okay? So just going strictly to the right. And I just need to make a quick but very useful observation about subsequences. If you have a subsequence of a sequence and you go out to the kth element of your subsequence, then that's bigger than or equal to k. Okay, so in other words, so the kth element of your subsequence is always further out than the kth element of the sequence itself. Okay, and that sort of just follows straightforwardly from this intuitive picture, right? So like the first term in your subsequence, you can pick to be any term whatsoever. So n1 is always at least as big as 1, right? You can't go further to the left than that. And then the next thing in your subsequence, you can jump over any amount that you want, right? So you could, if you only jump over 1, if you're starting at A1, you could jump over to A2, but you could also jump further than that, right? So your N2 is always going to be at least as big as A2. And it's only going to be A2 if your first element of your subsequence was A1 and you only jumped over by 1. Right, so since you can jump over as far as you want, you don't have to jump over by 1, and you're free to pick wherever you start. Your subsequence, the kth element of your subsequence is going to be further along than k itself. Okay, so this n2 here is at a5, so that's so your n2 is 5 here, that's bigger than or equal to 2, and your n3 is 6 here, that's bigger than or equal to 3. Your n4 is 8, that's bigger than or equal to 4. Okay, so kth element of your subsequence is always further along in the sequence than the kth position in the sequence itself. All right, so hopefully that makes sense. So the first thing we're going to do with subsequences after the definition examples is we're going to prove a little theorem, which should be intuitive. A subsequence should sort of inherit properties from the sequence itself. In particular, if the sequence is converging to something, then the subsequence should be converging to the same thing, right? Because it's rather intuitive. If your original sequence is sort of getting arbitrarily close to some real number a, then your subsequence is your subsequence going along the same sequence is just skipping things. So those elements of your subsequence have got to be getting arbitrarily close to a as well. You can think of a picture. So if you have your limit a here, your sequence is getting arbitrarily close to a, right? But your subsequence is just going to be going along that same sequence, just maybe skipping some. So instead of hitting all of these points, we might skip some, but we're still sort of traveling down the same road that the sequence itself did, right? So you can imagine somebody walking down a road with normal paces, right? They're going to heading towards some destination. Well, if somebody walks down that same road but is taking big leaps, right, doing 3 or 5 steps, to the original person's 1, they're still going to be heading to the same destination along the road, right? They're still going to hit the same destination. So that's the basic idea. So the theorem here is that subsequences, and I'll just write this down and then come back. Okay, so we have a subsequence of a convergent sequence. It converges to the same limit as the original sequence. So let's take a look at the proof. So we're going to suppose, so we have a convergence sequence. And then, so suppose that and let a sub n sub k be a subsequence. subsequence. So the claim is that this thing converges to A, right? So we need to let epsilon greater than 0 be given. We're doing a convergence proof. So let epsilon greater than 0 be given. And then the point is, well, after some point, after some big N, right, this A little n's are, within any prescribed distance of A, right? But if we go out to A sub little n sub big N, right, right, so what we have is A sub big N is bigger than or equal to big N, right, by that fact we proved up here, by that fact we discussed up here. The N sub k's, that's bigger than or equal to K. Okay, so in other words, if we go out to capital N and beyond in our original sequence, well, if we go out the same number of terms in our subsequence, well, we're only going to be even further along, right, down the road. So you can imagine your guy, taking normal steps, right? He's taken some number of normal steps, and then he's within, whatever prescribed distance of his destination. Well, somebody taking much larger steps, right? If they take the same number of much larger steps as the original one did, they're going to be even closer to the goal, right? So that's the basic idea. So then there is big N such that little n bigger than or equal to big N implies that that A sub n is within epsilon of A, then if K is bigger than or equal to big N, and so K, this is measuring the number of giant steps that we're taking in the subsequence, right? So as long as we take at least as many giant steps as we had normal steps up here, then we should be, even closer to the goal. So that should work. If we take our K bigger than or equal to N, we have that A sub N sub K, right? A sub N sub K is bigger than or equal to K, which is bigger than or equal to N. So, right, since, or sorry, not A sub N K, just N sub K. So we have N sub K is bigger than or equal to K is bigger than or equal to N. So A sub little nk is within epsilon of A. All right, so this N sub K is one of these n's that's bigger than or equal to N, right? So we have this inequality for that value. Okay, so that completes the proof there. So just a note about this. So basically the logic of this is that AN, right, so if you have your sequence converging to A, then that implies that a subsequence, A sub nk, also converges to A, but the converse is not true. Okay, so the theorem, logically speaking, just kind of looks like that, but the converse is not true. Okay, so you can consider the sequence 0, 1, 0, 1, 0, 1, 0. All right, so this is going to be a divergent sequence, right. I mean, so I think we've seen this sequence before. Maybe make it 1, -1, whatever. We proved a sequence like this doesn't converge, but it has convergent subsequences, right? So you have this convergent subsequence of ones. You also have a convergent subsequence of zeros, and but that does not imply that the original sequence converges. Okay, and in fact, I mean, we can use this theorem to show that this doesn't converge, right? That this original sequence doesn't converge, because what we have is we can use the contrapositive of this theorem. Okay, so so by the contrapositive, so applying contraposition to the theorem, we have the following divergence criterion. Okay, so so here's the divergence criterion. It says that if we have two subsequences which converge to different limits, then the original sequence must be divergent, right? Because our theorem says that if we have a convergent sequence, then every subsequence must converge to that same limit, right? So the negation of every subsequence converges to the same limit is that there's at least two different subsequences which converge to different limits. Okay, so what we find is this divergence criterion. So as an example of this, if we have x not equal to y, real numbers, right, then we can consider the sequence of alternating x's and y's. Right, this is not convergent, or is divergent. Right, because you have this subsequence of just constant x's converging to x, subsequence of constant y's converging to y, and they're not equal. So since their subsequences are converging to different limits, our original sequence must be divergent. And so last thing I want to talk about real quick is this theorem here. One more kind of cool application of this theorem. So here's an example. This is just an application of the theorem in green. And what we're going to do is so say you have some x between 0 and 1. If x is between 0 and 1, then the limit of the x to the n's is equal to 0. This is something we proved by looking at the infimum of the set of xn's and showing that that infimum is 0. We did that, I think, a couple lectures ago. But there's a really slick proof here using the notion of subsequence and the fact that subsequences have to converge to the same thing as the sequence itself, and also the monotone convergence theorem. So first note that what we have is x that's bigger than x squared, that's bigger than x cubed, that's bigger than x to the fourth, that's bigger than ... etc. Right? And of course all of these are greater than 0. So I should say, so my ... is bounded below by 0. So our sequence, x to the n, is monotone and bounded. So the monotone convergence theorem, that implies that it has a limit, right? So implies that the limit of x to the n is some L, right? So this limit exists. Okay, so that limit must be something, and then the claim is that that L is equal to 0. And there's a really slick, proof. So the proof is that the subsequence, so if I consider just the even, the x to an even power, so x to the 2n, must also converge to L. So also have convergence to L. Right? But what we can do, however, we can also compute, and so if we look at the limit of this x to the 2n, that's equal to L, as we just said. but x to the 2n is x to the n times x to the n. So this is the limit of the product of two sequences. Right, so you have the x to the n sequence multiplied by itself. And from the algebraic limit theorem, right, since we know this x to the n, this is a convergent sequence, I can apply, right, the limit of the product is the product of the limits. So this is the limit of x to the n times the limit of x to the n. Okay, so this is by the algebraic limit theorem. Algebraic limit theorem. And of course, that's just L itself, right? This is L times L. This is L squared. Okay, so therefore we find that L is equal to L squared. And of course, that implies that L is equal to 0 or 1. And we know that the limit, right, the limit has to be, by the order limit theorem, right, the limit L has to be less than x. So, but L is less than x, which is less than 1. And so that implies that L is equal to 0, as claimed. Pretty cool, right? Pretty slick. So you might remember our original proof that x to the n goes to 0 when x is between 0 and 1 was a little bit clever and used the existence of the inf. This proof is clever in a different way. And again, it uses the monotone convergence theorem, right? So the monotone convergence theorem really comes from the existence of sups and infs. So that's kind of built into this slick calculation here. So it's more or less kind of the same ingredients going in, but it looks a little bit different. All right, anyway, that's it for this lecture. And in the next lecture, we'll discuss another property of Koshi sequences about how when a subsequence of a Koshi sequence, right, when a subsequence converges, then the whole sequence has to converge. So that sets Koshi sequences apart from general sequences, right? Just having a convergent subsequence doesn't mean that the original sequence converges in general, but this actually does hold for Koshi sequences. I'm trying to go back up to our list. Yeah, so that's what we'll prove next time. We'll also prove Boltzano Virustras and then wrap up by just discussing why the Koshi criterion follows from that, which we sort of already discussed in this video, but I'll remind you of that in the next video as well. All right, that's everything for this lecture.